Assalamu alaikum class, welcome to week number 5. First of all, Ramzan Mubarak to everyone. Today we will talk about chapter number 10, which is error detection and correction. First we will talk about introduction to error techniques, then we'll talk about type of errors, then we try to understand what are block codes, linear codes, checksums, cyclic codes, and at the end we'll discuss about the forward error correcting codes using Hamming. So let's start the lecture. First we will try to understand why detection and correction of errors are important. So we start with why error detection and correction. As I have mentioned earlier in the lectures, because of the attenuation, noise and interferences, some errors will definitely occur, and this will lead to the corruption of some of the bits, which are transmitted bits. And particularly, there are two parameters which are very important. Number one is the frame size, and second is the probability of single bit error. Obviously, if the transmission media is noisy, the probability of single bit error will be more. When we are sending data in the form of a frame, the size of the frame will also decide the probability of error in a frame. That means these two parameters, frame size and single bit error, will decide that whether we are receiving a frame with error or without an error. And it has been proved mathematically that the longer the frame size and higher the probability of single bit error, lower is the probability receiving a frame without error. That means the probability of receiving a frame without an error will increase with the increase of the size of the frame, as the probability of the single bit error increases as well. If the frame size is long, when we have a long sequence of zeros and ones, then one of the bits will get corrupted, the interframe will have an error. This clearly emphasizes that the need for error detection and error correction for the communication in a reliable manner. Then we have to devise some schemes so that errors which are inevitable can be corrected. So let's check out the various schemes. Let's first consider types of the errors. This is called a single bit error, where only one bit gets corrupted. This is the binary of the ASCII code. So this 7 bits is representing a specific ASCII code, and the second one is representing some other specific ASCII code. So if there's an error occurs, so it can be interchanged if there's a single bit error. This is very common in parallel transmission. Similarly, let's suppose if we are sending 8 bits in a parallel, so we got 8 lines. And when we are sending an 8 bits, then if one of the line is faulty, when a line is faulty, the signal passing through the line may cause an error. Other lines may not have error. This may lead to a single bit error. This is how single bit error occurs in a parallel transmission if one line is faulty. Then there's another type of error which is called burst errors. It occurs whenever there is more than one bit get corrupted. Let's suppose you are sending a long sequence zeros and ones. So what can happen here? The duration of noise is longer than duration of the one bit. Let's suppose the duration of noise, this is the duration of noise, is covering at least 4 bits. So there is a possibility that some of these bits may change during the transmission. So out of these 4 bits, the 3 bits have got corrupted. So leading to the signal which is faulty or the other end. This is called multiple bit errors, and we call it a burst errors because there's a bursty noise which is responsible for this type of errors. And this is common in serial transmission. Well, you are transmitting serially, then during transmission, the transmission line may suffer may be exposed to some kind of fluctuations of electrical equipments, or maybe because of electrical disturbances, maybe possible lightning. Any of these reasons, multiple bits may get corrupted, because the duration of the noise is longer than the duration of one bit. So what we need to do is to develop a technique that will not only detect single bit but can detect burst errors. So how it's been done? We have to use a redundancy. What is a redundancy? Let's suppose this is your message. It may comprise of several bits in sequence. We need to put some additional bits which are called frame check sequence. So this thing which is added, and then we will send the transmission. This is the frame check sequence, and we call it redundancy, and this becomes a part of the message which is being sent. And these additional bits can be used for detection, and we can also correct the errors. There are certain mechanisms we'll discuss later. Obviously this FCS is a function of, FCS will be dependent on the message. So this frame check sequence will be calculated based on the message, and then it is sent to the receiver, and the receiver will check the message and the frame check sequence to detect if there is any errors. The popular techniques you can see here are simple parity check. A single bit is added. We have two-dimensional parity bit to enhance the parity. Third technique that is called is checksum. Checksum adds several bits to detect errors, and checksum bit error detection is much better than the first two. And finally we'll discuss about the cyclic redundancy check, which is very popular, and this is the most sophisticated and best for detecting errors. So let's talk about the parity check. It is the most simple and the most popular detection scheme. What it does is append a parity bit to the end of the data. Let's suppose we are sending a character 1011001. So there are 7 bits. So we can add a parity bit, and the parity bit is added. Well, it is based on whether you are using an even parity or an odd parity. If you are using even parity, including that bit, the number of ones should be equal to even. So we have 1, 2, 3 and 4 even. So parity need to be 0 here, because it will make even number of ones inside. In other words, even number of bits in a message. Similarly, if you are using odd parity, then we need to add 1 at the end. So we have already discussed synchronous asynchronous modes. In asynchronous we use usually odd parity, and in synchronous modes we usually use or even parities. So let's see how is it exactly done. This is the basic scheme of parity check. So this is the data 1011011 that need to be sent. We need to compute a parity bit. As we can see here, we have got odd number of ones, so we add 1 at the end, which is the parity, to make the message even. So the data along with the parity bit is sent through the transmission media. When it is received at the receiving end, so the receiver check all the bits whether they are even or not. If it is even, it will accept the data. If it's not, then it will reject the data, which is number of bits are odd, that will reject the data. That means some errors are occurred which have led to the single bit error. This is the basic scheme of using a parity check. And obviously to compute the parity bit in both cases can be done exclusive OR. So let's check the performance of simple parity check. Here all single bit errors are detected. It can detect all single bit errors, and also it can detect burst errors too. If it can only detect burst errors if the number of bits in the error is odd. So if the number of bits are even, then if one bit is changed, If one bit is changed to 1, another bit is changed to 0, then the corruption is there but we cannot detect it. The simple parity check cannot detect it. So we find that this technique is not fruitful in burst errors if there are more than one error. If an even number of bits are inverted due to error, the error is not detected by using this simple technique. To overcome this limitation, we can use two-dimensional parity check. In two-dimensional parity check, the performance is improved by using two-dimensional parity check. So we organize the data in blocks of bits in the form of table. So here it is organized in a table that will be two-dimensional. So parity checks are calculated for each row, which is equivalent to simple parity check bit. Each row has a parity bit. So parity bits are also calculated for all the columns as well. So we have a parity check for each of the rows and parity check for each of the columns. Then both are sent along with the data. And at the receiving end, they are compared with the parity bits calculated on the received data. So let's check example. What exactly how it works. So this is the original data. Here we have divided data into 4 octets, which are called blocks. So we have 4 blocks or segments. Then they are organized in the form of table. We got 4 rows, which are basically belong to the segment. For this particular row, the even parity is calculated with 1, 2, 3, 4, 5, and this is the 6th bit. So we have done for each of the row similar thing, similar method. Then the columns are calculated, the parity bits are calculated, and even parity is added at the end. So for each of the columns, the total number of ones we will calculate, and we'll see if it's odd or not. If it's odd, then we add 1 to make it even. So the last one, the rows, the parity of the parity is calculated, which is in column. So we can see that we sent 4 segments of data, each of 8 bit. That means it's a 32 bits. Earlier using the checksum itself, and to send that, the total number of additional bits now after adding the parity, these are basically 9 bits are here, and we have 5 blocks. So 9 into 5 is 45 bits. So the redundancy is above at least 13 bits. So we can see here the overhead is much more than a single parity check. If we compare it on multiple columns and rows, then we have at least 45 bits. And obviously we do it to achieve better performance. The overhead is traded for better error detection capability. How? For example, it can detect not only the odd number of bits, but also it significantly improves the error detection capability compared to simple parity check. It can detect burst errors, but not all. For example, let's check the example again. Let's suppose if these 2 bits, even number of bits get altered, and in the second row these 2 bits are altered, the 4 bits are changed, then this column parity bit can be used to detect errors. So now let's check the third scheme, which is the checksum. So in checksum, at the sender's end, again the data is divided into k segments, each of m bits. Just like the two-dimensional parity bit, here also data is also divided into segments. So for example, we have taken the same example from the previous one, which is two-dimensional parity bit. So we got 4 segments, and each of bits are called m bits. Here what we do is we add the bits in the segments, and as we know, when there is a end around carry, it is added with the least significant bit to get the sum. So we have 2 segments, the third segment is added. There is no end around carry here, So there's a partial sum, then the fourth segment is added. There's an end round carry as well here after adding the two. So in this we will get the partial sum. So this partial sum which we'll get 1000111. So this partial sum is now taken complemented of to get the checksum. So here we get the checksum, which is the opposite or complemented of the sum. So this checksum is sent along with the four segments. Along with the data segments, we are sending a message segment equal to m bits, which is now received at the receiving, and the receiver will check in the same manner. All the received segments are added and using one's complement arithmetic to get the sum. So we have one additional step. So we assume here that there is no error taken here. So 1, 2, 3 and 4, these segments are added. So we get the partial sum of them all. So we have the fourth segment. So the additional segment, which is checksum, it is added with the sum. So we'll take the complement. If the result is all zeros, then we assume that there is no error has taken place, and the conclusion is to accept the data. If there is an error in the complement, then we will not accept the data. So now let's check the performance of the checksum. Like the simple parity or the multidimensional, it can check all the odd number of bits. Here the performance is same as a simple parity check. However, it can detect most of the errors involving even number of bits. So this means that the burst errors can be detected. So we find the performance of the checksum is comparable to two-dimensional parity check, and overhead is little lesser than the two-dimensional check. With single parity we have 32 plus we have 8 bits, which is 40 compared to 45 in case of multi-dimensional parity check. So we have some extra overheads but less than the two-dimensional parity check. Now let us come to the cyclic redundancy check, which is the fourth scheme and the final scheme for detecting the errors. Cyclic redundancy check, what we do here, it is one of the most powerful and commonly error detection codes. We will see why it is so. Why cyclic redundancy check give you best performance in terms of error detection quality. The basic approach, given a m bit of bit sequence, the sender generates a n bit sequence additional bits known as frame check sequence FCS. So each of m bits, which is a block, an additional n bits sequence is calculated based on some scheme, so that the resulting scheme, the frame will consist of n plus m bits, which is divisible same predefined number. So we are using a predetermined number which is known to the sender and receiver both. So let's check out the example. If here we got a data of m bits and then we add some additional n bits which are all zeros, so this is divided by n plus 1 bits. So this is a divisor. So this is which is chosen very carefully, and both sender and receiver knows this divisor, and it gives you n bit data. If we divide a number n plus 1 bits, we'll get the remainder, which is n bits, and this bit is called CRCs. They are called cyclic redundancy check bits, and these zeros are replaced by CRC when we are sending the data. So we send data plus CRC. This is what is being transmitted on the transmission media. So at the receiving end, the receiver receives the n plus n bits, data plus CRC. It is again divided by the divisor. So as we have already told you, the divisor has to be known by both receiver and the transmitter. And after division, it generates a remainder. If the remainder is 0, then we accept the data as a correct data, else we will reject the data. And this is based on modulo 2 arithmetics. Let's see how we perform the arithmetic 2 on CRC. It's based on modulo 2 arithmetic division. And how it is done, as we can see through this example. So let's assume we have a data 4 bits and we have a divisor 1011. So the data are 4 bits are only, for the simplicity, can be 8-bit, 16-bit, 24 or 32 bits. As we know, the divisor is n plus 1 bit, so we add 3 bits with the data for division, and it is divided by the divisor. And the division process is simple. So the quotient is there, so we do it by ones, so 1011 is down there. So we get the remainder after division, which is exclusive OR division. So we got 001. So 0 at the end comes down to make it 4 bits, because we can only divide 4 bits. We can't divide 3 bits with 4 bits. So the quotient is there 0 again, so we add 000 because the first bit is 0. And first bit is 0 again, so we'll add quotient 0. At the end we can see the 0 comes down as well. So we add 000 again. And we do the exclusive OR and we'll get the answer 100. Then last 0 comes down here and the quotient comes 1. 1011 comes down there, so 11 is 0, 000, 01 is 1, 01 is 1, and the remainder is 011. So the remainder has to be 3 bits, and this remainder is basically the CRC, which is actually connected with the data and it is sent to the receiver. So you see we saw the division of the modulo 2. So at the end of the division we got the remainder, and it is connected with the data. It is divided by 1011. If we do the division the same way, we will get the remainder, which is 011 in this example. So here we have generated CRC, and we will do the similar process in the receiving end to see if the data is correct or not. So the polynomial, if we have a sequence, is 1 1 0 0 1, it can be represented as a polynomial dummy variable x as x4 x3 plus 1, because the first bit corresponds to x power 0, second x power 1, third is x power 2, fourth is x power 3, 4 is x power 4. So the zeros does not appear in the polynomial, whereas 1, only the value of 1 appear in the polynomial. So x to the power 0 is 1, so we have 1, x3 and x4. So we find that this is more concise way of representing the bits. The division can be expressed as, that is, the message is comprised of m bits, mx comprises of, which is multiplied by x to the power n, we got m plus n bits. That is then being divided by polynomial. As we can see, that we will get remainder, and that remainder is used as a CRC, check bits. And there are some standards polynomials based on some mathematical properties. These are used for the purpose generating CRC check bits. Let's say CRC16, it is used in ATM, asynchronous transmission mode. Here it has a degree of 16, but only 4 factors are here. CRC CCI is used in many applications. It has a degree of 16. It has 4 factors as well, and it should not be divisible by x and should be divisible x plus 1. So these are the 2 minimum properties. Should not be divisible by x, should be divisible by x plus 1. And based on this thing, we have CRC32, which is used in Ethernets. So we have a degree of 32 here. This is a concise way of representing the bits in the form of polynomials of the dummy variable x. Now, how do you really perform the division in a reality? using the electronics in receiving and transmitting end. This can be done using a hardware called linear feedback shift register LFSR, which has a feedback. This register can be used frame check sequence of the CRC. Also at the receiving end, it can be used to check the received information is correct or not. And this linear feedback register has n number of flip-flops and at most XOR gates. So XOR gates can be less, but the flip-flop has to be there. So we devise a polynomial, a suitable chosen divisor polynomial, and it has to be of degree n. So it will have n flip-flops, and then we'll see how we can constitute using a frame check sequence. So now we will see how we can apply this LFSR in a hardware. So this is a polynomial character of degree 3, which is x cube, x and x plus 1. Since it is of degree 3, so the number of flip-flops will be 3. 1, 2, 3. C0, C1 and C2. 3 flip-flops and 2 exclusive OR gates, which are linked with 1 and X. X3 is the feedback. So we don't need any more exclusive OR. So we just need 2 exclusive ORs gates. So this will make the necessary hardware for performing the hardware division. So this is the initial condition where all flip-flops are 0. Make sure to understand one thing, that C0 is lashed with C1 and C1 is lashed with C2, and C2 output is lashed with the exclusive OR gates, and we can see the input. So the input will first come to the first exclusive OR, which is then moved on to C0, and then there's another 0 there, and then the exclusive OR will be done and the output will be moved on to C1. So since these outputs are directly connected to C2, C1 output is connected with C2. So we will see how this thing actually moves on. So just do the exclusive OR and see the process. So first clock is applied. C1 will come here, C0 will come here, C1 will come here after applying first clock. Apply second clock, we will find that this 0 will come here, this one will come here, this 0 will come here. We can apply all the 7 clocks because we got 7 bits. So let's apply the 7 steps or 7 clocks and see how this thing goes actually. This 0 comes here, this 0 comes, this one comes here, and finally we apply the final clock, so we get the final CRC, which is 0, 1, 1, and we got 7 steps. After applying 7 clocks, we got the CRC 0, 1, 1, which are actually in the flip-flops. So there to be sent is 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1. Now the receiving end, instead of applying the input, the receiver will apply the sent data as input to the same registers, and then it will apply the 7 clocks, and it will be seen that the result will be all zeros. And if there is an error occurs, then this end result will not be 0, 0, 0 and will be something else. So this is how the polynomial division is performed by using a linear feedback. Let us see the performance of the CRC. CRC can detect all single bit errors. This is similar to parity check, simple parity check. It can detect all double bit errors provided there are 3 ones in the polynomial. As we have seen the characteristic polynomials, if the number of ones are more than one, then we can detect all double bit errors. we can detect odd number of errors as well if they are divisible by x plus 1. NCRC is chosen as it is divisible by x plus 1, so we can detect single bit. So we can see that the CRC can detect single bit, double bit, but it can also detect burst errors which is less than the degree of the polynomials. So if the degree of polynomial is n, it will detect all the burst errors of the degree less than the degree of the polynomial. We have seen in CRC are using 16-bit or 32-bit. In this case, we can find 15 burst errors. Similarly, we can find most of the large burst errors, that means up to 15 bits. When the polynomial is of degree 16-bit, we can detect at least 15, then the number of burst errors more than 15 bits can also be detected. In other words, most of the larger burst errors more than 15 bits can also be detected with a high probability. For example, with CRC12 we can detect at least, which has 12 degree, we can detect 99.97% of errors with the length of 12 or more. So we find that the CRC gives you a very powerful error detection scheme, and that is the reason it is so widely used. Now let's move on to the last topic, and it's called error correction. We have two basic approaches. The first approach is backward error correction. This backward error correction is based on when the error is detected in a frame, the sender is asked to retransmit the data frame. That means the receiver will check the error, detect the error from one of the schemes that we have discussed, and send the information to the sender and ask the sender to retransmit the frame once again. This is called automatic repeat request, and it is called backward error correction. And this particular scheme will be discussed in our next chapter. In this lecture we will discuss forward error correction. In this type of error, what we do is like we use more redundancy in the transmitted data to not only detect but correct error in the received data. So error correction is there. It is based on the received data. We don't ask for retransmission. We detect the error and we correct the data on the receiver side. So let us see the basic idea. The basic idea is to have more redundancy, in particularly by using distance. For example, whenever you are performing error detection, the requirement is an error detecting code if and only if the minimum distance between any two code word is 2. So what you can do is all the codes can be identified into two groups, which are like two sets. One is called code word and other is non-code word. Then when you choose two code words, say you're choosing this one, another code word must have a distance of 2. What do you mean? That the 2-bit positions can be differ, like this one here. So these two positions are different. This is called distance of 2. And any error occurs in any of these two code words, it will fall in non-code word. It will not be part of code word, it will be part of non-code word. However, any single bit error will lead to non-code word. So the codes are selected in such a way that they differ in number of bits. If we check the codes which are generated by the parity bit, we will find that this property is satisfied. That means any two code words will differ in two bits. But error correction requirement is more. The minimum distance between any two code words must be more than 2, and the number of additional bits should be such that it can point to the position of the bit error. So the requirement is not only interested in detecting the error, but identifying where the error has occurred. So the additional bits are needed to be selected in such a way it is possible to point the error bit in the error. So the requirement is, if k additional bits are used, then it can point to 2 to the power k positions, and the requirement is that 2 to the power k has to be more than 2 m plus k plus 1. Only then the error correction can be done. So the table here shows, so we can see the number of data bits. If they are 7 bits, so we need to enter the redundancy bits, which can be 2 to 4. For one data bit there has to be 3 bits, but for 7 data bits there need to be 4 positions, which will add a redundancy of 4 and makes it 11. So let's suppose if we have 16 bits, we can assume that it may require a 5 bits. So that means there's a m plus k, which becomes 21. So 5 redundant bits. So 5 redundant bits are added with 16 bit data. That will make it 21 bits. So we will see how it's done. So the basic approach. So k parity bits added to form m plus k code bit. And the location of each code, m plus 1 digits, is assigned a decimal value. Then the k parity bits are placed in a position 1 to 2 to the power k minus 1 positions. So the k parity checks are performed on selected digits of each code word. At the receiving end, the parity bits are calculated. The decimal value of the k parity bit provides a bit position in error, if any. So let's see how this thing is actually done. So calculating the Hamming code. The key to the Hamming code is the use of the extra parity bit to allow the identification of single error. Create the code word as following, that is 1010101, and then we need to find a position in between those bits for the parity, and the position for the parity is always set as 1 to 4816, which is power of 2. 1 to 4816, 32 64, and it goes on as long as there's a data. All other bit positions are for the data to be encoded. Each parity bit calculates the parity of sum of the bits in the code word. So instead of the data, we'll make it a code word. The position of the parity bit determines the sequence of bits. So the position 1, to mark the position 1, which is of parity, we need to check one bit and skip one bit. That means we will check the data 1, then the data bit 3, data bit 5, 7, 9, 11, 13, 15, and so on. Second position is of parity as well. So what we'll do is, like, we'll check 2 bits and we'll skip 2 bits. So check 2 bits, skip 2 bits, etc. means 2, 3, and then so it will start, the position 2 will start from the 2, and we'll check the 2 bits 2, 3, and leave the 2, that is 4 and 5. Then check 6, 7, 8, 9 left, 10, 11 is checked, 12, 13 is left, and 14, 15 is checked. So similarly we do the same process for the position 4, position 8, position 16, and position 32. So we set the parity accordingly. So let's check out the example. Now we know where we have to set the parities on position 1, 2, 4, 8, 16, and so on. So if we have a data, let's suppose we have a data of 4 bits. Let's assume that we have 1, 0, 1, 0. So what we need to do is we need to set the parity bits P1, P2, P4, 1, 2, and 4 position. So we have data bits 1, 2, D3, and D4. Then as you can see that we need to set the parity position 1. This is position 1, position 2, position 3, position 4, position 5, position 6, and position 7. And so we have 7 positions by adding 3 parities. And the codes are shown here. So if we, on position 1, if we have 0, 0, 0, that means we have no error. If we have 0, 0, 1, that means it has an error in position 1, 2, and then error in position 3. So these parities are calculated. So we use 1, 3, 5, and as shown in previous slide. P2B has been calculated by 2, 4, 2, 3, 4, 5, we leave 4, 5, 6, 7. Position 3 will be calculated, start from the 4, 5. We leave 8, 9, 10, 11. So let's calculate P1. So we have 1, 3, 5, 7. We are using even parity, so there are 2 ones there. So there we will put 0 there. So in position 2, we will check out the positions. So we make it even. 1 we will add 1 to make it even. In position 3, so we have even. So we'll put position 3 as 0. So this check is done after receiving the data. So the data becomes of 7 bits instead of 4 bits. So during transmission, if we find out that 1 bit is changed, let's suppose the error is occurred in position 5. So the data will become 1, 0, 0, 0, 0, 1, 0. And now if we will check the parity position 1, and we'll say 0, 0, 0, 1. This means that the parity position 1 is not even and it is odd. So what we'll do is like we'll add 1. We need to have a 1 in parity position 1. So we'll put 1 here by checking the positions. Similarly for position 2, we'll understand 2, 3, 6, 7. This makes a parity even. So this is fine. So we'll put a 0 here for position 2. And for the position C, for the position 3, we'll check 4, 5, 6, 7 and we'll say it's odd. So we'll put 1 here. So by adding the 3 parity positions becomes 5. And the 5 is the corrected data. So we'll write it again. 1, 0, 1, 0, 0, 1, 0. So we see that with this simple example, we illustrated how we can correct the data using Hamming code, and this is called Hamming code scheme. And this is how we do the correction at the receiving end. So thank you very much for watching the video. Till next time, take care and Allah Hafiz.